The Foundations of Geometry by David Hilbert. Chapter 4, The Theory of Plane Areas. Section 20, The Measure of Area of Triangles and Polygons. Definition: if in a triangle ABC having sides A, B, and C, we construct the two altitudes h sub A equal AD and h sub B equals BE, then, according to Theorem 22, it follows from the similarity of triangles BCE and ACD that we have the proportion A is to h sub B as B is to h sub A. That is, we have A times h sub A is equal to B times h sub B. This shows that the product of the base and the corresponding altitude of a triangle is the same whichever side is selected as the base. And half of this product of the base and the altitude of a triangle delta is called the measure of the area of the triangle delta, and we denote it by f of delta. The segment joining a vertex of a triangle with a point of the opposite side is called a transversal. A transversal divides the given triangle into two others, having the same altitude and having bases which lie in the same straight line. Such a decomposition is called a transversal decomposition of the triangle. Theorem 29. If a triangle delta is decomposed by means of arbitrary straight lines into a finite number of triangles delta sub k, then the measure of area of delta is equal to the sum of the measures of area of the separate triangles delta sub k. Proof. From the distributive law of our algebra of segments, it follows immediately that the measure of area of an arbitrary triangle is equal to the sum of the measures of areas of two such triangles as arise from any transversal decomposition of the given triangle. The repeated application of this proposition shows that the measure of area of any triangle is equal to the sum of the measures of area of all the triangles arising by applying the transversal decomposition an arbitrary number of times in succession. In order to establish the corresponding proof for an arbitrary decomposition of the triangle delta into the triangles delta sub k, draw from the vertex A of the given triangle delta a transversal through each of the points of division of the required decomposition. That is to say, draw a transversal through each vertex of the triangles delta sub k. By means of these transversals, the given triangle delta is decomposed into certain triangles delta sub t. Each of these triangles, the delta sub t, is broken up by the segments which determine this decomposition into certain triangles and quadrilaterals. If now, in each of the quadrilaterals, we draw a diagonal, then each triangle, delta sub t, is decomposed into certain other triangles, delta ts. We shall now show that the decomposition into the triangles delta ts is for the triangles delta sub t as well as for the triangles delta sub k, nothing else than a series of transversal decompositions. In fact, it is at once evident that any decomposition of a triangle into partial triangles may always be affected by a series of transversal decompositions, providing, in this decomposition, points of division do not exist within the triangle, and further, that at least one side of the triangle remains free from points of division. We easily see that these conditions hold for the triangles delta sub t. In fact, the interior of each of these triangles, as also one side, namely the side opposite the point A, contains no point of division. Likewise, for each of the triangles delta sub k, the decomposition into delta sub ts is reducible to transversal decompositions. Let us consider the triangle delta sub k. Among the transversals of the triangles delta emanating from the point A, there is always a definite one to be found which either coincides with a side of delta sub k, or which itself divides delta sub k into two triangles. In the first case, the side in question always remains free from further points of division by the decomposition into triangles delta sub ts. In the second case, the segments of the transversal contained within the triangle delta sub k is a side of the two triangles arising from the division, and this side certainly remains free from further points of division. According to the considerations set forth at the beginning of this demonstration, the measure of area, f of delta, of the triangle delta, is equal to the sum of the measures of the area, f of delta sub t, of all the triangles delta sub t, and this sum is in turn equal to the sum of all the measures of area of f of delta sub ts. However, the sum of the measures of area f of delta sub k of all of the triangles delta sub k is also equal to the sum of the measures of the area f of delta sub ts. Consequently, we have finally that the measures of area of f of delta is also equal to the sum of the measures of area f of delta sub k. And with this conclusion, our demonstration is completed. Definition. If we define the measure of area, f of p, of a polygon as the sum of the measures of area of all of the triangles into which the polygon is by a definite decomposition divided, then upon the basis of Theorem 29 and by a process of reasoning similar to that which we have employed in 18 to prove Theorem 24, we know that the measure of area of a polygon is independent of the manner of decomposition into triangles, and consequently is definitely determined by the polygon itself. From this we obtain by aid of Theorem 29 and the result that polygons of equal area have also equal measures of area. Further, if P and Q are two polygons of equal content, then there must exist, according to the above definition, two other polygons, P' and Q' of equal area, such that the polygons composed of P and P' shall be of equal area with the polygons formed by combining the polygons Q and Q'. From the two equations, f of p plus p' equals f of q plus q', f of p' equals f of q', we easily deduce the equation f of p is equal to f of q. That is to say, polygons of equal content have also equal measure of area. From this last statement, we obtain immediately the proof of Theorem 28. If we denote the equal bases of the two triangles by G and the corresponding altitudes by H and H' respectively, then we may conclude from the assumed equality of content of the two triangles that they must also have equal measures of area. And that is to say, it follows that 1/2 GH equals 1/2 GH'. And consequently, dividing by 1/2 G, we get H is equal to H', which is the statement made in Theorem 28. The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice. This ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Wrenholt. Programming and illustrations by Jim Wrenholt. 2019. Portrait of David Hilbert by Reida Wrenholt. Thank you for listening.